Alright, let's talk about groups of order 60. This part's going to be a little time consuming, and it's going to combine a bunch of results from the book into one. But it's a pretty interesting theorem, so let's have at it. First, the number of Sylow 5 subgroups you can check should either be 1 or 6, because of course it has to be a divisor of 12, and yet it also has to be congruent to 1 mod 5. And so those are the only two options. Well, if it's the case that it's 1, then there exists a normal subgroup of size 5. So let's focus on 6. Let's assume from now on that n5 is equal to 6. So what do subgroups with 6 Sylow 5 subgroups look like? What do groups of order 60 with 6 Sylow 5 subgroups look like? Well, let's look at the next prime, 3. So what can 3 look like? What can Sylow 3 subgroups look like? Well, how many can there be? Well, it has to be a divisor of 20, and it has to be congruent to 1 mod 3. So what are the options there? Well, there's many. You got 1, 4, 10, and then that's it. What happens at 1? So let's assume that n3 is 1. Well, that would mean that there's a normal subgroup of size 1, 3. Well, then G mod H has size 20, which is 2 squared times 5. Well, by the Sylow's theorem, G mod H has a Sylow 5 subgroup. Right? More importantly, based on the previous video, this is something of the form p squared times q. And q is not congruent to 1 mod p. Wait, hold on, let me think about that carefully. This is that one case where if you look at nq and you ask, is it equal to p squared, do you actually get 4? Well, it turns out this is that case where that can't happen. Because remember, when we did that calculation, it turned out that the only way that ever happened is if p was 2 and q was 3, and we're not in that case. So not only does it have a Sylow 5 subgroup, but that Sylow 5 subgroup is normal. And by the isomorphism theorems, we know that subgroups of quotient groups correspond to subgroups of the original group that contain the group you're quotienting by. Moreover, this relationship preserves normality. So you now have a normal subgroup of G, such that when you quotient by H, you get this normal subgroup of G mod H. Moreover, how big is n? Well, it's size 15. So what is n? It's a group of order 15. We've already discussed, that means it's the cyclic group. And it's normal in our group G. Oh look, 5 is one of the divisors, so n has a Sylow 5 subgroup. Moreover, it's a normal subgroup of G, so it's closed under conjugation. So actually n has every Sylow 5 subgroup from G, because it has at least one of them. So this is a general fact that's worth noting: if you've got a normal subgroup of a group G, and P is any Sylow P subgroup, and P is a subset of N, then obviously you're going to get all the conjugates to be in there too. And so why do I care about that? Well, because we're in this case where we're trying to assume that n sub 5 is 6. So that means that we've got 24 elements here of order 5. In this group, that's isomorphic to Z mod 15. You can see the contradiction. This isn't possible. There's too many elements. So there's a contradiction here. Alternatively, we have these 6 Sylow 5 subgroups that are subgroup of N, but N is isomorphic to Z mod 15Z, which has only one subgroup of order 5. So this isn't possible. So what must the contradiction be? Well, it can't be the case that n sub 3 is equal to 1 and n sub 5 is equal to 6 simultaneously. You can't have this. Which means if n sub 3 is equal to 1, then n sub 5 is equal to 1. So if you have a normal Sylow 3 subgroup, then you have a normal Sylow 5 subgroup. Oh, okay. I guess that's information. All right, now let's look at N2. What are the options for N2? Well, it's going to have to divide 15, and it has to be an odd number. So we see the options are 1, 3, 5, or 15. Again, what happens at 1? So here we're assuming N5 is 6, but N2 is 1. That means that we have a normal subgroup of order 4. Well, what's G mod N? It has size 15. It's isomorphic to a cyclic group again, which means, of course, it has a normal subgroup of order 5. Which means that G has a subgroup that's normal of order, let's do the math, 5 times 4, 20. Of course, by Sylow's theorem, H has a subgroup of order 5. So H contains at least one of the Sylow 5 subgroups of G. If we're assuming H is normal, it contains all of them. So we see H contains every Sylow 5 subgroup. So this should look very much like deja vu. It's essentially the same argument we just had. But we have the same problem as before. There's only one Sylow 5 subgroup in a group of order 20, and it's normal. So we can't have all 6 of these things because there's only one, so there's a contradiction again. And so we discover that if N2 is 1, then so is N5. So what we're getting is if G has a normal, any normal Sylow subgroup, then it has one of order 5. This allows us to prove a theorem that the book mentions. If G is simple, or no wait, if n5 is greater than 1, then G is simple. Of course, we prove the contrapositive if there exists a non-trivial normal subgroup of G, which is not the identity and not the whole group, then n5 is 1. As you can tell from what we've done so far, all we really have to show is that there's a normal Sylow subgroup of some kind. And that's not too hard to prove, because what do we know about n? Well, we know it must divide the order of G. And so n must factor as 2 to some a times b, times 3 to some b times 5 to some c, where a is between 0 and 2, b is between 0 and 1, and c is between 0 and 1. And they're not all 0, and they're not all the rightmost numbers. And so, of course, Sylow's theorem would tell you that this group has to have one of these. It has to have a Sylow 2 subgroup, a Sylow 3 subgroup, or a Sylow 5 subgroup. In particular, what do we get as the possible values for n? Either it's going to be 2, 3, 4, 5, 6, and then let's see, that's 4 times 3, then 10, 15, 20, definitely got 30 in there, and I forgot 12. Okay, now we've got all the numbers. Now, of course, you can go back through and recognize that either you've got primes, squares, or products of distinct primes. If you go through these, you'll discover that each of these corresponds to one of the cases we've already covered. And in each of these cases, we discovered that there was a normal Sylow P subgroup. And assuming for the moment that you end up getting, let's ignore the cases with just 2's for right now. We'll come back to that. In other words, if you're a multiple of 2, then you're actually a multiple of 4 for your order. There's a reason I'm excluding that for right now. Then, in fact, your Sylow P subgroup is a Sylow P subgroup of your larger group, and by the previous lemma we've already stated, you must contain all of the Sylow P subgroups, which means that there's only one Sylow P subgroup in the larger group, and therefore it's a normal Sylow P subgroup in the larger group, and then this lemma applies. So the only cases that are harder are when you're talking about 2, 6, 10, and 30. And you're talking particularly about the Sylow 2 subgroup. But in these cases, you can check that actually you have a normal Sylow 3 subgroup, a normal Sylow 5 subgroup, and a normal Sylow 5 subgroup. So then the only issue is when you have this normal subgroup is size 2. In all other cases, you're guaranteed to have a normal Sylow P subgroup where P is of the same order as the Sylow P subgroup in G. So what happens when n has size 2? And it's normal. Well then, G mod n has size 30. And as we've already discussed before, that implies that it has a normal subgroup. That's isomorphic to Z15. Which means that you now have, going back to the original group, you now have a normal subgroup of size 30. Congratulations. You're back in one of the other cases we already covered. So there you have it. If you have more than one Sylow 5 subgroup, then you're actually a simple group. So the groups of order 60 come in two types. Either you have a normal Sylow 5 subgroup or you're simple. Note that if you check the proofs in the book, I have a lot of the similar arguments, but in some places I do things slightly differently, so it's worth doing the comparison. Both the textbook proof and my arguments rely on working a lot with the Sylow subgroups and then working a lot with the previous cases. The only difference is I fully point out this lemma here and do the argument slightly differently. But that's because I was trying to not assume the result from the beginning, or I was trying to just study Sylow subgroups from the get-go to lead to this theorem rather than just starting with the claim. There's actually more we can say. If you have a group of order 60 and it's simple, then it's actually A5. So we've already shown A5 is simple, and we now just showed that if n the number of Sylow 5 subgroups was 6, then it turns out you must be simple. But not only are you simple, you're actually A5. And yes, it turns out A5 has 6 Sylow 5 subgroups, namely the 6 subgroups generated by the 5 cycles. So the proof goes in stages. First, we're going to note there does not exist a subgroup of small index 2, 3, or 4. And the reason why this is because if there was, you just let G act on the set of cosets. By left multiplication, this would give rise to a permutation representation. And the kernel of this action would be the largest normal subgroup. So this is a theorem in the textbook we did not prove. But the kernel of such a homomorphism is the largest normal subgroup. That's a subset of H. But, because H is a proper subgroup of G, and because we're assuming G is simple, it must be the case that it's the trivial group, which means that this is injective. So, phi of G is isomorphic to a subgroup over here, and in particular, G, which is 60, has to divide G mod H factorial. But, 1, 2, 3, and 4 factorial are not divisible by 60. So this is not possible when this is 1, 2, 3, or 4. It is possible when it's 5, so that tells you it is theoretically possible to have a subgroup of index 5, but nothing smaller than that. In fact, index 5 is what we're going to need. So now we look at N2. Before, we've studied that it can be either 3, 5, or 15. Note, of course, it's also, whatever it is, it's the index in G of the normalizer of the corresponding of any corresponding Sylow 2 subgroup. And so what this calculation tells us is that 3 can't be an option because there's no subgroup of index 3. But 5 and 15 are options, and the first part of the proof is to study the case 5. So 5 says there's a subgroup of index 5. So in particular, letting H be this Sylow P subgroup and acting by left multiplication on the cosets, we now have a permutation representation of G as a subgroup of S5, and it's injective. So G is a permutation group on S5. Oh, that's kind of what we want. So now we just have to show that it's actually A5 itself, that the image under this map is A5. So we're going to identify G with its image under that homomorphism. So it's now a subgroup of S5. Well, we can ask, and it's a subgroup of order 60, and we can ask, well, is it possible that it's not a subgroup of A5? Well, then what's G times A5 going to be? I mean, by definition, this is a set that contains A5 as a subset, but well, A5 is a normal subgroup, so actually this is a subgroup of G that contains A5 as a subgroup, and it's contained in G. I mean, it's contained in S5, the larger group. And so, if we're in the case we're assuming that G is not equal to A5, this left-hand containment can't be true, so it must be the case that G times A5 is S5. So here's G, here's A5, here's their product. The index is 2 by the diamond isomorphism theorem. G intersect A5 as index 2 in G. But this contradicts what we just said earlier, which is that there's no subgroup of index 2, 3, or 4. So this part can't be true. So G is a subgroup of A5, and G has size 60. So G is actually equal to A5. So congratulations, under this isomorphism, G is isomorphic to A5. So we see that when n, the number of Sylow 2 subgroups, is 3, then we're isomorphic to A5. Of course, we still have to see, let me state that correctly. When the number of Sylow 2 subgroups is 5, then we're isomorphic to A5. We still need to deal with what happens if the number of Sylow 2 subgroups is 15. Now remember, Sylow 2 subgroups have order 4, because the largest prime power of 2 dividing our group is 4. And so we want to actually rule out and prove that no such group exists. And the first thing to try is to consider the case, what happens when, for all such groups, their intersection is the identity element. Because remember, I've mentioned before, in these cases you just can't count elements and their orders willy-nilly. You have to be a lot more careful about it. One way to be more careful about it is to add assumptions like this. First, suppose that they all intersect trivially, so now when you count the number of elements in each subgroup, you can do it separately. So there's 3 elements in each of these subgroups. It's not the identity, and there's 15 such groups. So you get 45 elements in these Sylow 2 subgroups. When you add that to the 24 elements of order 5, you get too many. So that's enough to tell us that there's Sylow 2 subgroups with a non-trivial intersection. Well, let's let M be this normalizer in G of this non-trivial intersection. Because we note, of course, M, if this thing were all of G, then that would imply that P intersect Q is a normal subgroup. But of course, we're assuming our group is simple, so it must be the case that M is not G. Since P and Q both have order 4, they are actually abelian groups because there's only 2 groups up to isomorphism of order 4. And so P and Q are both subsets of M, which means that 4 divides M, which implies that this group has to be of size bigger than 4. Why bigger than 4? Because it contains the elements of P and the elements of Q, so it contains at least 6 elements. In fact, you can say it's at least 6. And so we have a group of our total order is 60. We can't have index 2, 3, or 4, so 30 is index 2, 20 is index 3, 15 is index 4. These are not allowed as options. And so we need to be a multiple of 4. It looks like 12 is the only option left, because 8 is not a divisor of 60. So we see M has order 12. And index 5. Oh, so we can have G act on G mod M and get a permutation representation inside S5 like we just did before. And you go through the calculations we just did, and none of them actually relied on the fact that P was a Sylow subgroup. It only relied on the fact that it had index 5 and that there were no subgroups of index 2, 3, or 4. And so, in fact, you now see yet again that G has to be isomorphic to A5. Of course, this is a problem because you can prove that and the number of Sylow 2 subgroups in A5 is 5, not 15. So you end up getting a contradiction anyways. So starting off with the assumption that there were 15 Sylow 2 subgroups, we actually proved that there were 5 Sylow 2 subgroups. Whoops! So no such group exists. Although it's worth completing the proof. Why are there 5 Sylow 2 subgroups in A5, where you're looking for 5 subgroups of order 4? It's not too hard to check that our favorite Klein 4 group is still in here. The other 4 groups essentially correspond to replacing one of these numbers with 5. So you pick one of your favorite numbers, replace it with 5. That gives you one distinct group. There's 4 possible ways to do it. It gives you 4 different groups. Each one of them contains only even permutations. Each one of them is isomorphic to this one, so they are the same group. So there's the 5 different Sylow 2 subgroups. And so you see that this is true. You also see by that fact that according to the Sylow theorems, those groups are all conjugate to each other, so this group is not normal in A5. Which makes sense because A5 is simple. But this gives you part of the reason why this is true. Just because this was a normal subgroup of A4, and A4 is a subgroup of A5, did not mean it's normal in A5.